Alright, let's go ahead and talk about 7.5, the unit circle. So we're going to talk about, well, what is the unit circle? How is this useful for us in terms of trigonometry? And we're also going to see how is this actually pretty much the same thing that we've been doing, just through a different point of view. So to start us off, let's go ahead and introduce the unit circle more or less formally. So for the unit circle is, well, a circle, no surprise, that is centered at the origin, so the point 0, 0, and that has a radius of 1. So remember, radius means that if I start at the center of the circle, and then if I go to any edge of my circle, that distance is my radius, or in this case, radius 1. And you can see here, as I go from the center to any edge of my circle, the distance stays the same. So this is what we call the unit circle. You could also say that this is the circle centered at the origin with a diameter of 2, because diameter is twice of the radius. Alright, so what's going on with this unit circle? And how does this relate to our trig functions that we are familiar with? So what I'm actually going to do here is I'm going to use a different definition for all of my trig functions. So we know that from before, we said that with a right triangle, sine of theta was opposite over hypotenuse and all these other formulas for my 6 trig functions. But let's talk about our new definition here. I'm going to go ahead and say let sine of theta be y over r, and I'm going to talk about what these letters y, r mean, and x as well. Cosine be x over r, tangent be y over x, cosecant be r over y, secant r over x, and cotangent is equal to x over y. So I'm going to claim that these are two alternative ways, well not two, another alternative way to look at my trig functions. So for example, if I look at these points, I see the letters y, r, and x. What do these letters mean? Well, you can probably guess that r represents the radius, or in this case, whenever I'm talking about the unit circle, remember we said that the radius is always 1. And then x and y. So x and y, this is actually going to come from an ordered pair. Remember, whenever we plot an ordered pair, it's something like, for example, 1, 2, or in other words, x, y. So we're going to use those terms to help us figure out what these trig values are. Now let's go ahead and actually show you the more detailed unit circle. Here I have our huge unit circle with all of these different angles and these different x, y points. So if I wanted to look at, for example, sine of 30 degrees, how can I use this unit circle to figure out what sine of 30 degrees is? Well, we know how to do this from before on a 30, 60, 90 triangle. We could use that method. But again, today we're looking at an alternative way to deal with sine of 30 degrees. And depending on your preference, you might use the unit circle method, or you might stick to the right triangle method. Whichever is your own preference. We will soon learn that they're actually the same thing, just from a different point of view. So sine of 30. What I'm going to do is I'm going to locate 30 degrees on the circle, which I can very quickly find to be right here. I can tell already that I know it's going to be in the first quadrant, so I know that that's where I was starting to look. Alright, so if I look at this 30 degrees, I have its equivalent in radians. So if I want to talk about this in terms of pi's, this is pi over 6. And this correlates to the point the square root of 3 over 2, comma, 1/2. So this point that I have here is actually the point that lies on the edge of my unit circle. You can see that there is a little dot here. So this is some things that are related to what we know about the unit circle. So I know that sine is supposed to be the y value over r. Well, what's my y value? My y value here is 1/2. And what's my r, the radius? Well, if I'm working on the unit circle, my radius should be 1. So I have 1/2 divided by 1, or just 1/2. So we have sine of 30 degrees. And if you use the right triangle method from the previous lectures, then you'll find out that yes, this should be, in fact, 1/2 if you want to double check. So this is how we think about the unit circle. What if I want to talk about something else like cosecant of 240 degrees? Well, I know before if I use my right triangle method, I would have to start off by figuring out what's my reference angle, what quadrant am I in, so that I know if it's positive or negative, and all of those other things. But if I use a unit circle, just like before, let's look for 240 degrees. Let's see, 240 degrees. Here we have it on the bottom left. And I know that cosecant is r, the radius, over y. Well, we know what r is. On the unit circle, r is always equal to 1. And what's my y value? Well, my y value here is negative square root of 3 over 2. And now I have to clean this up, because I don't want a fraction within a fraction. To clean this up, we're going to do our keep, flip, change rule. Anytime I divide by a fraction, I keep the top portion. I flip my bottom fraction, and I change to multiplication, giving me 1 times 2 over negative square root of 3. We know that multiplying by 1 doesn't really change anything for us, so I'm left with this, negative 2 over the square root of 3. Notice here that I put the negative to the left. You could have kept it on the bottom. These are all equivalent forms. That is, they mean the same thing. Alright, so last thing that I want to mention here, before we get to the final simplification of this, is that notice that there's a square root on the bottom, and we know that we don't like having a square root on the bottom. So we have to rationalize. That is, I'm going to take the square root of 3 and multiply it by the square root of 3 over the square root of 3. Give me negative 2 square roots of 3 over 3. So this is my cosecant of 240 degrees. I want to remind you again that yes, we could have used our old method with the right triangles as well. If we use my old method with the triangles, the special right triangles, I would have to look at 240 and figure out the reference angle. You would find out that the reference angle would be 60 degrees, because that's the closest that we are from 180. And then you would say cosecant of 60 degrees. What does that give us? Furthermore, we would also notice that this is in quadrant 3. If you remember, our all students take, only tangent and cotangent were supposed to be positive. So yes, we were expecting cosecant to be negative. So once again, I've said it multiple times already. This is actually the exact same final answer as if we used the special right triangles and the quadrants. This is just a different way for us to solve it. Alright, so we've done cosecant of 240 degrees. One other nice thing about this unit circle is that this lets us work with the quadrantal angles as well. We couldn't really do the quadrantal angles with our special right triangles, but with the unit circle, I have my 4 major quadrantal angles, 0, 90, 180, and 270. Technically 360 and all of its multiples as well. But these 4 spots along my unit circle. I'm allowed to go ahead and figure out if I want to do sine of 0, secant of 180, cotangent of pi. I would pretty much just use the same idea as the previous 2 examples, where I did sine and cosecant, just with, of course, a different formula. So this is our quadrantal angles. Alright, so let's go ahead and do an example. Determine the values of these 3 trig functions if I'm telling you that we have this particular point, let's call it P, defined by the square root of 5 over 3, comma, negative 2/3. And I'm going to tell you that this point is, in fact, on the unit circle, and it corresponds to the angle theta. So, this one's a little bit different than the previous examples I did. Before I said give me sine of 30, what is that simplified, or tangent of 180, something like that. But what if I give you the point and I tell you it is on the unit circle? In other words, I gave you this point and it's not listed anywhere on our circle here, but it's somewhere along the edge of the circle. And that's going to be important for us. Since I know that this point is on the unit circle, then what is r, my radius of my unit circle? Well, whenever I'm working with the unit circle, my radius is always equal to 1. Alright, so let's go ahead and start with figuring out our 3 trig functions that we want. And for convenience, I've gone ahead and copied down these formulas from the previous slide. Sine being y over r, x over r, tangent being y over x. Alright, so for sine, what's my y value? Well, my y value from this point on the unit circle is negative 2/3. And right here, I spoke a little bit early, but just so that we know our x and y. We know that sine y is negative 2/3 and my radius is 1. And then dividing by 1 we know doesn't change anything. We still have negative 2/3. And that's already cleaned up nicely for us. What about cosine? Well, cosine is the x value, square root of 5 over 3, divided by the radius, which is still 1. So just for notes, I have the square root of 5 over 3, all divided by 1. Again, dividing by 1 doesn't change anything. I've got the square root of 5 over 3. And then the last trig function, we have tangent of theta, which should be the y value divided by the x value. Fortunately, we know what y and x are. Y is negative 2/3. X is the square root of 5 over 3. So I'm going to go ahead and plug in as needed. My y divided by x. Again, we have a fraction within a fraction, so we're going to do our keep flip change rule. I'm going to keep this entire top fraction the same, negative 2/3. I'm going to take the reciprocal, that is, I'm going to flip this bottom fraction to be 3 over the square root of 5. And instead of division, I'm going to change to multiplication. Giving me negative 2/3, again keeping this the same, flipping the bottom fraction, 3 over the square root of 5, and changing to multiplication. And now I can go ahead and try to clean this up. Well, the 3's can cancel each other out, because I have 3 essentially divided by 3, leaving me with negative 2 over the square root of 5. And unfortunately, we don't like having a square root on the bottom, so I have to rationalize again. And we'll do that by multiplying by the square root of 5 over the square root of 5, giving me negative 2 square roots of 5 all over 5. So I've gone ahead and found these three trig values given a point on the unit circle. A key point thing that I want to note here is that we were allowed to do this very quickly with R because I told you that we were on the unit circle. If I don't have these four words on the unit circle, then I have to figure out what R is technically.